So, welcome. Last time we formulated the problem of F divergence minimization by constructing the lower bound on it, and we saw that finally the problem, the optimization problem that we would be solving would be a saddle point problem, where you have to construct the lower bound on the divergence metric using the maximization, and that maximization is over a class of functions which we represented as t of x here. And once you construct the lower bound, that has to be minimized over the parameters of the sampler network g theta, right. So, finally, what we will have is a saddle point optimization problem. This is what I am talking about. Theta star is the minimizer, the set of parameters that would minimize the f divergence, and f divergence itself adheres to a lower bound, okay, which we constructed, that has an optimization problem over these class of functions which we represented as t of x. Therefore, the final optimization problem that we would be solving will be with respect to two set of parametric functions. Theta star, which is the sampler network, we will have to minimize the f divergence with respect to that, and we have w, which is the parameters of that particular parametric function that would approximate the t function that defines our lower bound on the f divergence. So, this is where we were last time, correct. Now, this time we will continue from those discussions, and I will show you how to realize that in practice. How do you actually solve that problem in practice using neural networks, okay. That is what we are going to do today. Remember, I called this the variational divergence minimization algorithm, VDM. So, we will have to implement the VDM using neural net. Okay. So, as discussed, we have two neural networks here. One is the sampler network, g theta network, that would take samples from an arbitrary random variable, Gaussian in our case, and transforms it into another distribution which we are representing as p theta, that is the so called generated distribution. And this neural network is typically referred to as the generator neural network, generator because it is sampling from the underlying distribution. And we have another neural network, TW, which is that neural network which is trying to approximate the t function. Remember, this t function is class of all functions that has domain as same as that of the data x, and the range of that function is domain of f star, where f star is the conjugate of the convex function that we started with, right. Now, last class there was a question that said, okay, in fact, yeah, I will have to, for the sake of completeness, I have to mention that after the class there was a question that was asked. Now, when we go from this step to this step where we are constructing the lower bound, when we put the supremum outside, it just does not become an inequality. In fact, if you look at my writing here, right, I have pushed the supremum outside and still kept an equality here, okay. So, this equality assumes that the class of functions that you are dealing with, script t, can have all those functions that would give you a pointwise solution for the inner supremum problem, okay. This becomes an inequality here, okay, the moment you assume that this script t, which is the bag of functions that you are optimizing over, may not have the solution for the inner supremum problem in a pointwise sense. That is when it becomes an inequality. So, this equality becomes an inequality because the class of functions that we are considering here may not have the solution for the inner optimization problem at all points, okay. Yeah, the reason I mentioned that right now is that now, since we are optimizing or rather approximating that t function using a neural network here, neural network in theory are universal function approximators, but when you are looking at a particular architecture, when you are having finite amount of parameters, then by construction it will not be a universal function approximator, and therefore the bound, the inequality that we have constructed over f divergence becomes a bound, because this neural network is restricted in the sense that it cannot approximate all functions to arbitrary closeness, okay. So, now, long story short, we approximate this t function using a parametric neural network, and this neural network is called the critique network or the discriminator network. I will tell you why historically it was called a discriminator network in a while, okay. So, let us call it critique network or approximator for the t function that construct a lower bound on the f divergence that we are trying to minimize, okay. So, now the problem is, yeah, so this is the objective function which has two expectations. Remember, our whole point was to convert that f divergence into an expectation over distributions that we have sampled from, so that we can approximate those expectations using sample averages. That was the whole point. Now the objective function has the difference between these two expectations. One is an expectation over Px, the other is an expectation over P theta. Let us represent that as j of theta comma w, because it is a function of both the parameters of the generator network and the critique neural network or the critique function. So the problem that we would want to solve is of this form, which is that we want to seek the minimum saddle point of this function, okay, or we want to solve this min max optimization problem where the maximization is over w and the minimization is over theta. That is the problem that we are trying to solve. Okay. Now, while we are solving this problem, how do you implement it is the question that I asked you, right? The first step towards implementing this is that you choose a particular f function. Because we are minimizing the f divergence, the first thing that we should do is that we should choose a particular f function. The moment you choose a particular f function, what would get fixed? What would get fixed is the domain of f star. So every f has a corresponding f star and it can be deterministically found out. The moment you define a convex function, differential or the convex conjugate of that function can be deterministically found out. The moment you find out what the conjugate function is, domain of f star gets fixed. Is that all right? So why is this of importance for us is because the t function that we construct for critique or constructing the lower bound has to be constructed in such a way that it respects the constraints on the domain of f star, correct? So once we choose the f function, f star gets chosen, and because of that the domain of f star gets fixed. Now how do you implement it in practice is typically it is implemented as follows. The t function, which is a neural network, is constructed as a composition of some particular function sigma f composed with vwx, some function vwx, where vw is a linear function or rather I should not be calling it a linear function, it is a neural network with linear activation at the last layer. It is from x to r, meaning you construct a neural network whose final layer is a linear layer, okay, which is that the range of this vwx function will be r, okay. And since the f function that we are looking here always have scalars as the range, so it is okay if you have r as the range of this linear neural network with linear activation, and then you compose that with sigma f, where sigma f is a function that takes r and projects it to domain of f, yeah, domain of f star actually, yeah, you understand. So basically you should think of it like this. This t function, okay, is a neural network that has a linear layer at the penultimate layer, and the final layer has an activation that will transform r into domain of f star. That is how you construct it. I mean, there is a reason why this sort of composition is done, because you know in the original paper that proposed this f divergence minimization, they would tell you what the sigma f are for a given f, so that the Lego block that you should always plug and play is this last layer's activation, so that it respects the domain of f star. Make sense? Okay, right. So if you write it that way, the objective function will now look like this, where the expectation of t of x would now be sigma f composed with vw of x, right, because that's the definition of t of x, right. Now this f star of t of x is f star of sigma f composed with vw of x, that's how it will look like. Now what we will do is we will look at one instantiation of this general idea of variational divergence minimization, which is called the generative adversarial networks or GANs in short. So to see interestingly, this idea of generative adversarial networks was proposed in 2014 as a standalone idea, okay, and then whatever we studied so far as the generalization of this idea as VDM came 2 years after that. Now in my narrative I have sort of inverted the story, because I prefer to see these things as specializations or special cases of this generalized algorithm, but historically it happened the other way around, okay. So these let's look at this generative adversarial networks as an example or an instantiation of this particular framework called VDM. So as I said, you start with a choice of an f divergence. In this particular algorithm called GAN, the f divergence or the f function that is chosen is this u log u minus u plus 1 log u plus 1. This is similar to Jensen-Shannon divergence, not exactly the Jensen-Shannon divergence, because there is a constant factor that is there in JSD which is not there in this f function. Okay, so whatever the f function that was chosen that gives rise to the objective function in GAN is a convex function, of course, which is similar to the f function that is chosen in Jensen-Shannon divergence, but not exactly the same. Why am I saying this? Because it's somehow sometimes people tend to think that GAN is optimizing JSD. It is not optimizing exactly the JSD. It is optimizing an f divergence which is similar, which has an f function that is similar to JSD, but for a constant factor. Remember this. Now, once we do this, once we have an f of u, the next step is to find what f star of t is, right? We want to find the conjugate. The conjugate for this has this particular form. It's minus log of 1 minus e power t. So, this can be found out. You can take it as a homework, right? This is a standard problem in convex optimization where if you are given the primal convex function, find what the dual of that is or the conjugate of it. It is minus log 1 minus e power t. Now, because of this particular form of this function, domain of f star will be r minus. So, you will have to ensure that the neural network that you construct at the end of it will have this particular form. Okay. Now, if you have to ensure that domain of f star is this, the sigma f, the final activation function that we were looking at, will be minus log 1 plus e power minus v, where this e power minus v or minus v is the output of that v network. What is that v network? It takes x and gives you a real number. No, the neural network that has a linear activation at the end, right? That is what this v, a small v is. So, because domain of f star is r minus, the kind of activation that you would choose is minus log 1 plus e minus v. Okay. Okay. So, now if you plug in all these equations into our objective function and do some algebraic manipulations, the objective function will take this particular form: expectation of log of dw of x with respect to px and expectation of log of 1 minus dw of x p theta, where this dw of x is 1 by 1 plus e power minus v of x. What is v? V is that neural network that would take x and gives you a gives you a real number. Okay, that is vw of x. Now, okay, so why am I complicating things and why am I introducing one other function here dw is because, as I said, the original GAN paper writes this objective function in a totally different, from a totally different angle. I will explain what that angle is. What I wanted to show you was that the f divergence, I mean, or the lower bound that we constructed in terms of t function is exactly the same as this with different notations. That is the point that I am trying to make here. Okay. So, now this dw of x which figures in the objective function of adversarial network, generative adversarial networks, is simply 1 by 1 plus e power minus vw of x. Okay, which means that the critique network that we have now, or the critique function that we will have this vx followed by this as the activation function at the output. Now, this t network will be a composition of this v network, which is x to real numbers, followed by 1 by 1 plus e power minus vw of x, which is the usual sigmoid or activation function that we use in neural networks for classification. Make sense? Okay. So, now yeah, this is how the architecture for GAN looks like, right? The adversarial network looks like. You have this generator network, which is the same sampler that we have, and we have this so called discriminator network, okay, which is written as dw of x. What is this dw of x? It is the same tx that we had, but written as a composition of a linear neural network with linear activations at the end, composed with a sigmoidal activation at the final layer. Is it all right? Okay. Now, because of this, the output of this dwx network now is bounded between 0 and 1. Why is that? It's because the sigmoid function is bounded between 0 and 1, right? Now, since you are getting a number between 0 and 1 at the output of this t network that gives you the bound on the f divergence, this can be interpreted as a classifier, correct? So, it is a classifier. We will interpret that. I know you can interpret that as a binary classifier because it's giving you a number between 0 and 1. Are we good so far? So before we continue, any questions here? Um, Now how do you implement this in practice is that typically this g theta x network, the g theta of z network a function is a neural network. You can use any kind of neural network that you want, right? I mean, it can be a multi-layer perceptron, a fully connected neural network, or a convolutional neural network, or a transformer. It doesn't matter. It's the treatment that we have done so far is architecture agnostic. You can use any neural network. Similarly, for this binary, okay. By the way, since in this particular choice of f divergence, the T network can be interpreted as a classifier, people also call this a discriminator. A discriminator is a binary classifier, isn't it? So what does it discriminate between? I'll tell you that in a while. Yeah, so it's also called a discriminator network in this particular case. Otherwise, it's that critique network that would simply construct a lower bound on the f divergence. In this particular choice of f divergence, since the output of this network is bounded between 0 and 1, you can interpret that as a binary classifier, and hence the name discriminator. Okay. Once we do this, right, I'll give you a completely different interpretation of how you can see this as a classifier and so on. So just wait for that. Okay, so this is also another neural network. You can again have this as, with any architecture of your choice. You can make it a CNN, RNN, or MLP or anything. So we have these two neural networks, and we have to solve this saddle point optimization problem with this as the objective function. Are we good so far? Okay. So let us now see how to implement this particular thing in practice. Okay, when you code it up, how do you do this? What's the input that we have? If we have to write it as an algorithm, we have n samples that are drawn from px. That's our data. So if you want to make it concrete, let's say that we have MNIST data set with us, which are n images of these handwritten digits. So you all know what MNIST data set is, right? Is there anybody who does not know what MNIST is here? Okay, so it's the hello world of machine learning, right? So you have images of handwritten scanned digits. That's what MNIST is, and you have n. Let's say you have n samples of them. So how do you solve this min-max optimization problem? It is actually solved in an alternative manner. So first you solve the inner optimization problem, get the W star, fix that W star, and optimize over theta, and you alternate between these two. That is how this problem is solved. Okay. So now how do you solve the inner optimization problem to start with is that we need to solve argmax, we need to maximize this particular loss function, particular objective function. How do we do this? We have two expectations, 1 over px and 1 over p theta, and we know both of them can be approximated using sample averages. Let us say that you have b1 samples from px and b2 samples from p theta, where b1, b2 are simply batch sizes. So you have b1 samples from px and b2 samples from p theta. How do you get b1 samples from px? Just do a sampling from the n points that you have in the data set. That's your b1 samples. How do you get b2 samples from p theta? Sample b2 number of times the z from the normal distribution, pass it through that sampler network g theta, and you get b2 samples from p theta. Okay. So both of these expectations now can be approximated using these sample averages. So what was an expectation over log of dw of x now will be 1 by b1 times sum of log dw of xi. Okay. The second term will be 1 by b2 times log of 1 minus dw of xj cap. Do you see the difference here? The same dw function has to be evaluated once by taking xi as input and once by taking xj cap as input, x as input and x cap as input. So what is x and x cap? X is the samples from the distribution px, x cap are the samples from the distribution p theta. Are we good? Both of these terms with respect to the D network, where once we sample from px and pass it through the D network to compute log dw of xi, then we sample from p theta the distribution by passing the samples of normal distribution through g theta network and compute dw of x cap and compute the second term, add both of them, and then you do one back propagation or backward pass through the W network to solve the inner optimization problem. You note that there is a plus here because we are solving the maximization problem. Okay, so that is how you do one step through the TW network or the discriminator network. So once we have done that one step through the discriminator network, the other thing that we have to do is solve the outer optimization problem, which is a minimization problem with respect to theta. While we are doing this, we will have to keep the W parameters constant. So, you keep the W parameters constant. Now, we have two terms, but the first term, which is an expectation with respect to Px, is independent of theta, and that term can be taken off while you are trying to optimize the generator or the sampler network. The second term depends on theta, how? Through x cap. So, x cap is g theta of z, correct. So, now you sample from z, pass it through the g network, you get x cap. So, second term is what figures out when you are trying to optimize for the g network, okay. So, then you compute the second term, and then by keeping the W network constant, you do one gradient step through the theta network to solve the outer optimization problem and alternate between these two steps. So, that is how the VDM is trained in practice. Any questions here? Okay. So, if I have to summarize this entire training, right, in one slide, this is how it looks like. Yeah. So, first we train the critique or the discriminator network, keep the theta constant, okay, sample a batch of points from the normal distribution, pass it through the g theta network to get x caps, okay. Then you sample one batch from the true distribution Px, okay. By the way, people also refer to this as the true data and the fake data and so on. True data are the samples from the distribution Px, and the so called fake data is the samples from distribution P theta, okay. That's a terminology that is used. So, now get a batch of both the samples, pass the samples of the true distribution through the discriminator network to compute the first term in the objective function, and pass these the samples from the P theta distribution through the DW network to get the second term of the objective function, add them both, compute the gradient, do one backprop through the DW network and one gradient step to update the weights of the DW network. That is one pass of training of DW network, okay. Then to train the sampler network, okay, note that while we are updating the parameters of the sampler network, we do not need the samples from the true data. We do not need samples from the distribution Px. Why? Because the expectation of TW, the first term that is there in the objective function, is independent of theta. So, it will just go away. All we need are samples from the P theta distribution, again sample a batch of samples from the normal distribution, pass it to the G theta network, get samples from samples from P theta. Now, pass it through the discriminator network. So, note that while you need to do a gradient step through the generator network, you still need the discriminator network, because you need to compute dW of g theta of z. While you are keeping the parameters of the discriminator network a constant, you still have to pass the samples of x cap through the discriminator network to get this evaluated, okay, and then do a backward pass from where? From the output of the discriminator network all the way through the input of the generator network. Is that all right? So, if you are implementing these things in using frameworks such as PyTorch, etc., there is a way that you can keep the gradient of a part of a neural network not update. That is how you do it. So, while you are updating the G theta network, you make the gradients of the DW network not updatable. You just make it a constant and then pass the gradients all the way from the output of the discriminator network to the generator network, and then do one backward pass. So, what is happening is, when you have to update the discriminator network, there is one forward pass that happens through the generator network, two forward passes that happen through the discriminator network. Why? One to compute dW of x, the other to compute dW of x cap, right, and there is one backward pass through the discriminator network. This is while you train the discriminator. So, when you have to train the generator network, there is one forward pass through the generator network one forward pass through the discriminator network and one backward pass through the generator network via discriminator network, because the output is computed at the discriminator network. This is how you train it. Any questions on how do you do it? In fact, in tutorials these things would be shown, they are coded up and shown, and this is how you train it. See, typically when people train this, the generator and the discriminator network are not trained in the exact same ratio. It is not done 1:1. Okay, so we'll discuss why that is the case, but yeah, practically the way to do it is do one step through the naive way of doing it is through do one update step for the network, the parameters of the generator network, one update for the network of the parameters of the discriminator network, and keep alternating between these two, because you are solving the saddle point optimization problem. Now I told you that the moment you choose a particular f function, the kind of t function that we choose to construct the lower bound changes, and since it can be interpreted in a particular way depending upon what the domain of f star is, you can interpret the entire process of this VDM, variational divergence minimization, in a different way. That is what this algorithm called generative adversarial network does. As I told you, it is not projected as minimizer of the lower bound on f divergence. It is projected as a classifier guided generator sampler. Okay, and this interpretation is only true if we take that particular f divergence which is used in GAN, wherein the dw function or the t function becomes a classifier, or rather can be interpreted as a classifier. Okay, so now what I will do is I will show you that one interpretation that is possible when we make that particular choice of f divergence. And please note that this is not the general interpretation. If you change the underlying f divergence, the kind of interpretation is completely different, because the output of the TW function is no longer bounded between 0 and 1, and you cannot interpret that as a classifier. But for that particular choice of f divergence, you can interpret that as a classifier, and because you can interpret that as a classifier, the entire process of this training can be looked into in a different way, which we will see now. Okay. Okay. Now here is how to look at it. So now we'll actually derive the same objective function and the same we'll get into the same optimization paradigm from a totally different angle now. Okay, let's try to do that. Now let's say that we construct this type of a paradigm for sampling, which is that I know that if you start with an arbitrary random variable and then I make it go through a deterministic function, the distribution of the output random variable changes, and I also know that I can control the distribution of the output random variable by tweaking the function that I pass the random variable through. Okay. Now let us say that my goal is to ensure that the output of this function approximator p theta to go as close as possible to px. I will not talk about any divergence metrics now, okay, for now. Now let us say that there is a binary classifier that I have access to, and this binary classifier is classifying between the samples that are coming from distribution px and the samples that are coming from distribution p theta. Right. So every binary classifier, okay, can be seen as a discriminator between two distributions, right? What two distributions? So you can say, I mean, we have seen that in the previous course. So now p of y given x is what a binary classifier do. P of y equal to 1 given x is one distribution, p of y equal to 0 given x is the other distribution. So now here, suppose we have a binary classifier that would output 1 if the input to that is coming from distribution px, and it outputs 0 if it is coming from p theta. Okay. Now the question is, can this binary classifier be used to make p theta close to px as close to px as possible? This is the setting that we have, that we have a function approximator, okay, and we have a binary classifier that would classify between the samples of the true distribution and the distribution that is imposed by the output of this particular sampler. The question is, can we use this classifier to enforce p theta go close to px as much as possible. That is the question. Can you think of a method to do that? So, one idea is this, that you keep tweaking the parameters of the sampler, which is the function, okay, till a point where this classifier starts malfunctioning. When would this classifier stops functioning? It would stop functioning if it cannot distinguish between the samples of px and p theta. When would it not be able to distinguish between px and p theta? If px and p theta are the same distributions. Yeah, that is a good question. So, we do not know the classifier. So, that is why what we do is we alternate between finding the classifier and tweaking theta. That is how we get the saddle point optimization problem now. The question is, we do not know what the classifier is, because who gives us the classifier? We train it along the way, that is the point. But assuming that we have a classifier, I mean, I did not want to mix up those two ideas, right. The first thing is, assuming that we know what the classifier, we have a classifier that would classify between samples of px and p theta, we can perhaps use that in such a way that we keep tweaking the parameters of this generator function till a point where this classifier starts failing. The classifier would start rather the classifier would fail if both these distributions are indistinguishable indistinguishable with each other. That is the idea. Okay. Yeah. So, the answer is tweak theta, which is the parameters of g theta, till the classifier fails to distinguish between the samples of px and p theta, right. Okay. So, now there is another interesting idea. I mean, in fact, the question that he asked is very close to this. Now, does the failure of classifier always imply that px is equal to p theta? Can you think of failure modes of classifier, okay, or rather can you think of a situation where the classifier fails but px is not p theta? It turns out that we can. So, here is a pictorial depiction of what it is. I mean, I am just constructing a counter example here. Let us say that our px, let us say that our data is in 2 dimensions. So, x1 is x1 x2 are the 2 dimensions of data, and these points that I have marked with x are from px, okay, and let us say that my initial values of theta would give me points which cluster in this particular region in this space. So, initial theta would give me points here, and the actual px is here. Now, what do I have to do? I will have to tweak my theta in such a way that this cluster gets overlapped upon this particular cluster, isn't it? That is what I want. I want my p theta to become px, which means that the points that I am getting from p theta or the g theta network would simply overlap with the points with px, isn't it? Okay. So, and let us say that this is the classifier that I have, dw1 is the first classifier that I have, which correctly distinguishes between the points of px and p theta. Is it all right? Now, yeah, p theta 1, because we have started with the first p theta, right, we are tweaking it. Now, what am I asking? I am saying that move this p theta 1 in such a way that this classifier fails. I should just take this p theta 1 and move it to p theta 2. Now, if I move p theta 1 to p theta 2, would the classifier fail now? But did I make my px equal to p theta? So, here is a counter example that is telling you that making the classifier fail is not enough to make p theta and px overlap with each other, because the classifier, or rather the generator network, can adjust itself in such a way that it fools the classifier in believing that they are of the same class, but not coming from the same distribution. Okay. Now, what do you do? Suppose, I mean, okay, so p theta 2 is not something that we want. What should we do now? We will have to tweak the classifier. We will have to tweak the classifier in such a way that now it distinguishes between p theta 2 and px, which is now this dw1 now will become dw2, where this classifier now is able to distinguish between samples of p theta 2 and px. Now, keep doing this, keep playing this game, which is ask your classifier to ensure that it distinguishes between the points of px and p theta, and ask your generator to move your p theta in such a way that the classifier fails, and keep playing this game between these two networks. Does it make sense? See, If you read the GAN paper, this is how it presents it. Now, sounds like a nice story, but I am not convinced. I mean, if you tell me that okay, there is a divergence metric that I would want to minimize, and I construct a lower bound on it and then solve a saddle point problem, that makes sense to me. But now this, I mean, of course, it's this exact same thing that we are doing, but this interpretation is something that I am not a fan of, but it's there in the literature. Okay. So now how do we construct this? Hence the classifier has to simultaneously tweet along with the generator. The very exact question that he asked, right? We don't have the classifiers to begin with, and also making the classifier fail for a particular choice of theta is not enough to make px equal to p theta. So we have to keep alternating between these two. Make sense? So now how do we construct this? How do we formulate this mathematically? And by the way, this is called classifier guided sampler, where you have a sampler network and you are changing the parameters of the sampler network guided by a classifier. Hold on. So now all this works if you interpret your T network as a classifier. So suppose you change the underlying f function, none of this interpretation makes sense because it is no longer a classifier. So that is why you need to think in the most generalized sense, and all of these become special cases. Okay. Yeah, question? Good question. How do we know that it will converge? There is no guarantee whatsoever. The question is exactly the same as asking how do we know that constructing a lower bound on f divergence and minimizing it will actually lead to the actual minimum of f divergence. We don't. Now what is happening is your optimizer on theta is as good as the lower bound that you have constructed. Now if you construct a bad lower bound, then the minimizer that you are minimizing over theta will optimize for that bad lower bound. That is why you should, every time you solve the inner optimization problem, what you are effectively doing is to make that bound on the lower the f divergence tighter and tighter, hopefully. See, that is why training of this generative adversarial networks is not stable in the sense that it can oscillate between these two. There is no, because you are seeking for a saddle point here. Yeah. Okay. So if we have to formulate it mathematically, this idea of classifier guided sampler. So we have this DW network that takes that takes samples from the sample space of X and maps it to bounded 0 1. Now let DW represent the likelihood of sample X coming from Px. Let us say that this function DW represents the likelihood of a sample X coming from distribution Px. Remember what likelihood is? We represent likelihood using the density functions, right. So if DW is the estimator for density function right now because it is the likelihood. Now what is the objective? The objective is to maximize the log likelihood of X coming from Px. So if you want to build a classifier, okay, what should a classifier do? The classifier has to maximize the likelihood of a particular sample coming from class that is represented by sample 1, right, isn't it? If it does that, and if it is a binary classifier, because it is a Bernoulli distribution that it is trying to optimize, the other class will also be maximized. It will also maximize the likelihood that the sample is not coming from the other distribution, because 1 minus that is the likelihood of that. Okay, that is how it works. So the objective now is to maximize the log likelihood of this sample X coming from Px. How do we do that? dWx is the likelihood of X coming from Px. Log of that is the log likelihood, and I want to maximize that over W, okay, given that I take an expectation of all sample that is from Px. So this is the average or the expected log likelihood of X coming from Px modeled with dW. Do you see this? This term now is the expected log likelihood of the sample X coming from Px. All of you with me? Okay. I have to maximize that with respect to W, right, because my dW network or dW function is representing the likelihood of the sample X coming from Px. Make sense? Okay. Okay. Now classifier has to do one more thing, right? It should maximize the likelihood of X cap not coming from Px, or rather it is coming from p theta, it has to maximize the likelihood of x cap not coming from px, because we know that x cap has to come from p theta, not from px. Okay, what's the likelihood of something not coming from px? It is 1 minus dw of x cap, because dw is representing the likelihood of a point coming from px. 1 minus that is the likelihood of a point not coming from px. Okay, this is the log of the likelihood of x cap not coming from px, likelihood that x cap is not coming from px. You take an expectation over all samples from p theta and you maximize that with respect to w again. So this classifier has to do two things. It has to maximize the likelihood of a point x coming from px, and it has to maximize the likelihood of x cap not coming from px. It has to do both of them simultaneously, which is exactly this objective that we got. Now we have the objective function for this classifier. What is this classifier doing? This classifier is ensuring that the likelihood of a point x when it is coming from px is maximized, and the likelihood of a point x cap when it is not coming from px is also maximized. Basically it has to classify between the points of x and x cap, or the points from the distribution px and px cap, that is what px and p theta, that is what I was saying. Okay. Now this is the objective for the classifier. What should sampler do now? The objective for the sampler or the generator is such that the classifier has to fail, isn't it? So it has to ensure that the theta parameters of this the sampler has to be excuse me, tweaked in such a way that the classifier fails. What do you mean by a particular objective function failing? Now if there is an objective function and if there is an optimizer that is trying to maximize that objective function, just reverse the objective of that, and that is the failure mode of it, right. So therefore the parameters of this sampler network has to be constructed in such a way that the same objective function has to be minimized with respect to its parameters, and that is how you get the so called adversarial optimization problem. And the saddle point optimization problem or the min max optimization problem that we obtain is what gave it the name adversarial networks. Okay. So we got to the exact same point, right. Now this is classifier guided sampling, and this is true if and only if you choose that particular f function where the t function that we use for constructing the lower bound can be interpreted as a classifier. And as I said, every alphabet has a GAN associated with it, right. I mean, there is A GAN, B GAN, L GAN, X GAN, and etc. You can look at something like an LS GAN, what's it called? Lee-Source GAN, I don't remember what it is. So basically it uses an F divergence where the T function, right, becomes a regressor instead of a classifier. Least square GAN, yeah, LS GAN is least square GAN, right. So there you cannot interpret your so called discriminator as a classifier, and this story cannot be told. If you read the original adversarial network, generative adversarial networks papers, right, it will present this entire thing, this objective function in this particular way that I talked about. They say that, oh, there is a classifier and you need to construct the classifier which would maximize the likelihood of this, and then you have a sampler that would nullify the classifier. That is how it is presented. But remember what is happening. What is actually happening is that we are trying to construct a lower bound on the F divergence and then trying to minimize that lower bound that we construct, and we are alternating between those two. And the name adversarial comes because we are solving a saddle point optimization problem, that is it. And if you look at it from this neural network perspective, there are two neural networks. One is trying to be the adversary for the other, in the sense that one is trying to solve the opposite of the objective function that the other network is trying to solve. That's the point. Okay. Okay. So I'll show you maybe a couple of implementation special cases that are used typically in an adversarial network. I mean, I just want to ensure that that you people do not see this as a completely different thing or anything, right? So that's why I just wanted to make this talk about this. There's something called DCGAN. Okay, it's deep convolutional GANs. Not a complicated idea. So typically in a generative adversarial network or this VDM, what happens is the dimensionality of the the input random variable is much less than the dimensionality of the ambient data space that you are constructing in. So, that is because of something called manifold hypothesis that I will talk about in the next class, okay, when we look at the Versus-Steins matrix and so on. So, but typically this is the case where the dimensionality of the input random variable that goes as an input to this will be much lesser compared to the output random variable. So, in a suppose you are looking at image kind of data which has image kind of topology, and by the way everything that we did so far is agnostic of the modality, data modality. You can use the same idea with an image or with a speech signal or whatever modality that you are interested in. Now, suppose you have image kind of modality, which is the 2-dimensional or 3-dimensional grid kind of modality. People use these convolutional layers. So, that is why these convolutional neural networks are used anyway. So, what is done is that in a DCGAN, you start with a lower dimensions of the input random variable, and you keep increasing the dimensions of the generator network in the neural network in such a way that the output dimension matches that with the dimension of the input data, because the sampler or the sample space of p theta and px has to be the same, right. Finally, you need to get an image here at the output. So, to do that, people use what is called as transpose convolution or up convolution. Basically, the idea is that of upsampling, because you need to start with a lower dimensions and go to a higher dimensions, right. If you do that, you need to do what is called as upsampling, isn't it? And if you have to convert a vector into a grid of shape or tensors that have 2-dimensional topological shape or 3-dimensional topological shape, you use these kinds of activations or network activations called up convolutions or transpose convolutions. Okay, there is one nice archive article which is called Convolutional Arithmetic. It is a comprehensive document that talks about all kinds of possible convolutions, right, transpose convolution, 2D, 3D convolutions and all that. It is a handy document, you can have a look at it. So, this is what people refer to as DCGAN. So, deep convolutional GANs, and nothing changes from a theoretical standpoint, but what is done is that instead of having fully connected layers here, you will use transpose convolution or up convolution layers to ensure that the topology of the data is preserved, that is all. In fact, there is no need why one should do that. You can use a multi-layer perceptron and ensure that the dimensionality of the final layer matches with the number of dimensions in the actual data, and reshape your data in such a way that it starts looking like an image. That can also be done, but people have found out that empirically having a transpose convolution or an up convolution layer in the architecture itself will lead to a better sort of empirical result. That is it, there is theoretically nothing changes. Okay. So, one other important idea that would come recurrently in this course is how do you do sampling from conditional distributions. I told you that all the discussion that we did so far is for sampling from the marginals, isn't it? We start from an arbitrary random variable z and then we sample from px. Now, what if I want to sample conditionally from the conditional distribution p of x given y, where this other conditioned random variable y can denote a class. It can basically denotes any kind of semantic. As I told you, all these generative models that we see today, all these GPTs etc. and all that, the input prompt what we give is actually the conditioning, it is a sample from the conditioned random variable y. So, given that I want to sample from p of x given y is the question. The easiest demonstration of that is that you want to generate, let us say, MNIST kind of data conditioned on class labels. Now, if you construct a marginal sampler on the MNIST data set and do an inference on GAN, what you get are digits or images of digits, and you do not have control over what semantics those outputs will have when you sample. But if you want to have that control over what sort of digit is sampled, you will have to sample, you have to learn to sample from the conditional distribution. The idea is same across all kinds of generative models that we will see in this course, that instead of starting with samples of px, you start with samples from px y, the joint distribution or the conditional distribution, either of them. In other words, you need to have data which would have an image and also the class label. Whatever semantic conditioning that you would want to impose on generator, you need to have that sort of a data to start with. Okay, so all these image generators that you have seen in the in today's state of the art models, right, where you give a particular text and it will generate the image corresponding to that particular text, has been trained on pairs of images and texts. So there are lots of data sets. One famous example is this data set called COCO, common objects in context. Okay, so that has millions of images with the corresponding descriptions. So people have sat down and described what is there in the image. For instance, this is an image containing two people crossing the road with whatever the textual descriptions are. So all these models that you see today have been trained on that particular data set, which has pairs of the random variable that you want to sample from, and the conditioning variable as well. So that is the data, that is the kind of data that you would need if you want to sample from the conditional distribution. Okay, yeah. So example is x can be images and y can be class label corresponding to x, or it can be a textual embedding corresponding to x. Not told you what embedding is for now. Think of it like every sentence that is associated with an image can be represented as a vector. So that's what I mean by embedding. So because we cannot process natural text, right? What we need is real numbers. So if every text is represented as a real number, that is what I call by embedding. The kind of data that we should have is an image and the corresponding embedding, the pairs of them. Okay. The objective now is to sample from the conditional distribution P of x given y instead of sampling from Px. So the question is, how do we tweak the generative adversarial network or this VDM in such a way that it starts sampling from the conditional distribution. So the solution is to estimate P of x given y and make P theta approach P of x given y instead of Px. That's it. Okay. Can somebody suggest how to modify the whole framework to ensure that this would happen? Turns out that it's pretty simple. The way you should do it is that you concatenate the arbitrary input random variable with the conditioning random variable. That's it. You do the same thing with the discriminator. So what is happening is that the t function or the likelihoods that it is trying to maximize are the likelihood of co-occurrence of x and y. Okay. So now suppose your y is a class label in the case as in the case of MNIST, convert all those class labels into one hot representations, one hot embeddings, and take a z, concatenate that one hot embedding, and then feed that as an input to the generator, and do the same thing with the discriminator. That's it. Okay. So this keeps happening again and again. When we see the diffusion models, a similar kind of a thing happens. Basically the neural network that is trying to optimize the likelihood, it has to just see the random variable that you are sampling from along with the conditioned random variable. That's it. That is how it is modified. So now what do you do during inference? This is how you train it. Nothing changes. The only thing is every time it will either see the one hot embedding of the class, or it will see the textual embedding corresponding to that particular label, whatever the label the case may be. And then what happens during inference? During inference, this T network that we use to construct the lower bound is discarded. Yeah. So it's like that trusted friend or teacher that gets discarded after the job is done, right? So once the minimization is done, you don't need that anymore. In fact, one of my revered teacher used to tell me this, that the definition of a good teacher is such that he or she will become redundant after some time. So that is when, see, if a student is a student for the entire life and you keep teaching them the entire life, that's not the way to operate, right? You have to make your student independent. That's the idea. So discriminator does its job that way. Once it is done during inference, you completely discard it. It's not needed at all. What do? You sample from the arbitrary random variable and pass it through the trained G theta network. If you want conditioning, you also give that conditioning variable that is needed, and it can be a one hot label corresponding to that particular class, or it can be a textual embedding as well. What you get is the sample corresponding to that particular class label or the textual embedding, and if you have trained it well, then it should match with the distribution pH. That's the idea. Okay, so I will now stop this by just showing you. So there is this this website where people have trained a GAN. Okay, it's called thispersondoesnotexist.com. Okay, so what's happening here is every time I refresh, they are sampling from normal distribution and passing it through a trained GAN. It's not coming up. Why? Yeah, see this. This is the picture of somebody who does not exist. So it's actually the output of this particular GAN called style GAN, which is one GAN, one particular architecture that NVIDIA came up with. So every time I refresh this, this is sampling from unconditional distribution. Every time I refresh, a sample from the normal distribution is being fed through the generator, and what you see is the output of that. So none of these people exist apparently, right? So this is how you sample. So this is being sampled from the distribution of human faces, but these people don't exist. You can construct it, and this will be one of your first assignments, right, where you build a nice GAN on a. It only depends on your compute capacity now, right? If you have a good GPU, then you can have high definition data sets and train a style GAN. We have trained style GAN and you get similar results. We have seen that. Yeah. So every time I am refreshing, this is what is happening. You know, sample from Z, pass it through the generator network, and this is what you get. Okay, pretty cool, right? So the first time I still remember it, 2016 or sometime when I trained my first GAN on this data set called Celeba and started looking at faces of people. It's pretty fascinating, right? I went and showed it to my family members and all that. Said, so this is somebody who is not there, and it's unbelievable. This is the power of samplers. If you can estimate the underlying distribution well, and if your neural networks, the samplers are good enough so that they can estimate the underlying distribution well, and if you have enough data and good architectures, you can mimic human intelligence. That's what has been done with all these AGI, etc., and all that. No, yeah. So this is the adversarial way of doing it, or rather the VDM way of doing it. ChatGPT, etc., does not work with this particular generative paradigm. Those are the autoregressive models. We'll talk about that later in this course, but this is what it is. Yeah. So there is one other idea regarding related to the adversarial optimization. It's a different algorithm which is called the optimal transport (OT). It is also called Weierstein's matrix and Weierstein's GAN, because that also leads to a saddle point optimization problem. Okay, we will look at that. So F divergence turns out to be not the best metric because there is this problem called problem that rises because of the manifold hypothesis. We will talk about that, and the optimal transport is the next class of algorithm that we will look at, which will boil down to a very similar paradigm such as the adversarial networks or VDM, and then we will move on to the next framework of variational autoencoders and so on. Okay, that's it for today. We will meet the next time. Thank you.